Hello students, you've all been doing very well on the week 6 discussion, so we can go over this pretty quickly. So we've been talking about compound functions, in particular exponential functions. Exponential functions are those, as you know, in which the independent variable is given in the exponent, and you can see that in this equation here. This is the equation for the future value of an amount that you put into savings at a certain interest rate, or what you will owe if you take out a loan at a certain interest rate. Now note that this is an exponential function because the variable which is going to have the greatest impact in terms of what you get or what you owe is this variable x, which represents time. I would have chosen t to represent time, but because of certain Desmos limitations, calling it x makes it easier. The key piece to note over here is that all of this stuff over here is a constant. Okay, the interest rate and the frequency of compounding are for given savings account, they're fixed, they don't change, but the length of time for which you leave your savings in that account changes. Ditto for any amount that you may have borrowed. So this is an exponential function because the variable of interest to us, which is time, which is the independent variable, is in the exponent of this term, right, from here to here. This is the exponentiation sign. Okay, so let's go over to the graph which plots this equation, and we can look at it here. Now, the y here and the y here, they're two cases because you can then use different interest rates to see the impact of the interest rate on your savings account, right? Other than that, the two equations are identical. So let's take a look. In the first case, the interest rate is 3% per year, and in the second case is 1% per year. Note that the percentage value has been divided by 100 in order to convert it into decimal form here. Now you can see the two plots over here. Yes, the account with the 3% interest rate is performing better, but this is after a considerable length of time, right? It's almost 12.5 years here, 10 years here. Nonetheless, the higher interest rate account is performing better. Now let's see what happens when we increase the interest rate. As you can see, the curve starts to move up and curves up sharply. It is not increasing as a straight line. It's increasing at an increasing rate, right? So, which is why this is called an exponential function, because the exponent is in the, because the variable is in the exponent of the term, and it's making it increase at a rate that is greater than linear. Okay, so far so good. This is fairly straightforward. Now let's move along in the discussion to look at this piece related to logarithms. Logarithms are a little bit less common in everyday use. They're much more commonly used in engineering and science, but nonetheless they still show up. You may look at some of graphs in newspapers or magazines, and especially those related to finance, and maybe in some science magazines when they're showing certain quantities. And one of the axes will be plotting log quantities. So they do appear in everyday life, and you need to be able to know what the significance is. So let me come over to this graph, which plots a function, and then it plots the logarithm of that function. So now what I have here is this first equation written in the form of an exponential function, because this big C is equal to this particular term. So from what you've learned about logarithms, if we take the logarithm of both sides, we will get an equation like this. And then using the properties of the logarithms, we can write the exponent to the left-hand side of that term, and then just take the log of the remainder that's there. And so we get an equation that looks like so. Now the reason I want to point this out to you is if you note that this term C, big C over here, is a constant, It does depend on the specific case because that's where you pick the values of the interest rate and the frequency of compounding. But other than that, this is a constant. So compare this equation to the form of a straight line, which it shows y2 simply means it should be in the subscript, but the annotation software doesn't allow me to do that, so I'm simply writing it like this. So the second variable is equal to the slope times the independent variable plus another constant. This is a small c, big C and small c are not the same. Recall from your discussion of the straight lines that small c is the length or the span of the intercept on the y-axis where the straight line intersects the y-axis. Okay, so let's change the values of the variables a little bit and then see what happens. So I'm going to take r from the interest rate being equal to 0 to some larger value, okay? And so both the equation, the original equation, and the equation representing the logarithm of the original equation, you can see that both of them have plots that now look different. The value of the variable y goes up very rapidly in the original equation because obviously it's an exponentially rising function. But the value of the slope, or rather the value of the logarithm, goes up as well. So there are two things of note on this graph. The first one is that by taking the logarithm of an exponential function enables us to compress the display of that function, because both of these lines, the red solid line and the blue dashed line, are really representing the same function, right? I mean, you had that function y over here, which had this form. It was written out in its exponential form, and we plotted out its values. And then we just took the log of that function, right? So y2, as I mentioned over here somewhere, is equal to the logarithm of y, right? So when we plot that out, we can see that the y values, yes, which represent the log of the function, don't go as high. So if for some reason you're limited in space in displaying something, or you're displaying two quantities with values that are very far apart, by taking the logarithm of one of the quantities, you can compress its display and bring them both out into the same graph. So that's not necessarily terribly exciting, but it's useful. The other piece to note is that the information about the interest rate, which over here is in big C, capital C, which is the coefficient of the independent variable x, is now buried in the slope of this straight line, okay? Because remember, looking at the form of this equation, and here you can see that this entire term, multiplied by n, of course, corresponds to the slope of the equation. And recall that r was the interest rate in it. So now the interest rate information has been buried into this bit about the slope of the line. So it's a little bit more obvious that as the interest rate increases, we can see it here, that the slope will also increase. Well, you can say, what's the big deal about that? We can see that the curve is going up exponentially as well. That's true, but if you're comparing several curves, it may be useful to look at the straight line form as well. That is to say, looking at the logarithms of those curves to maybe get a more intuitive sense of the difference between them. Perhaps this may or may not be useful, but again, it's a useful thing to know that you can compress the graph, and then the slope of the resulting line, which represents the logarithm of the function, relates to its growth rate.